And we're live once again. Okay, so one of the most useful applications of the derivative, instantaneous rate of change, is when you're talking about the instantaneous rate of change of position. That's kind of what kinematic physics is all about, rates of change. It's what motivated Newton to actually discover the derivative. Speaking of Newton and his derivative, let's go on a little bitty tangent, if you will, here, and discover kind of the essence of what Newton did in his calculus. I'm going to show you what Newton did. Okay, this will be a nice segue into the motion. Let's say that we have a position function s of t, and let's just say it's t squared. Okay, something simple. Let's say we have something that's moving on a horizontal line, and its position at any given time t can be modeled by this equation. So at t equals 0, it's at 0. At t equals 1, it's at 1. At t equals 2, it's at 4, so on and so forth. Newton was trying to find its instantaneous rate of change, which ends up being the instantaneous velocity. Well, here's what Newton said. Newton said that we're going to let a little bitty piece of time go by, a little bitty piece of time. Okay, and he denoted that with a dot over it. He called that the fluxion of t. Okay, it's just a little bitty change in time. Very, very small. Well, if we have a very, very small change in time, we're going to have it manifest over here, right? That's the fluxion of t plus t squared. If I then evaluate that, I get t squared plus 2t fluxion of t plus the fluxion of t squared. Now, what do we notice about this? We notice that t squared is equal to this. So I'm trying to think of his mechanics here. What did he do? What did he do? I see the answer here. This. Oh, I got it. So this over here on this side here, that's going to end up being this. It's the original position plus a small change in the position as well. That's what that is. So if you let a little bit of t elapse, you're going to have to account for a little bit of change in the position. So it's the old position plus the fluxion of the position. Okay, so that's what it is. Now, what does that mean? We know that we have t squared on the right and we have s of t on the left now. And what happens with those two? They're the same, right? So Newton said that this and this will cancel. And the fluxion of the position, the tiny little change in the position, which Leibniz called the differential of y, the infinitesimal change in y, it's going to equal to 2t times fluxion of t plus fluxion of t squared. Now here's where Newton got clever, okay, as clever as he was. He said that the fluxion of t is essentially infinitely small. It is tiny. Now, if the fluxion of t is tiny, what is the fluxion of t squared? It's going to be even smaller. In fact, Newton said it was equal to 0. That's how small it was. If you take something that's infinitely small and you square it, it's going to equal 0. Now, what does that allow Newton to do in his mechanics? What can we do with this term? It goes to 0. And now he has the fluxion of the position equaling 2 times t times the fluxion of t. And Newton knew that he was interested in this ratio. He wanted the fluxion of position over the fluxion of time. Okay, that's what Leibniz was calling dy dt. Okay, that's what we're calling the derivative. So if you divide both sides by the fluxion of time, you get the fluxion of the position over the fluxion of time equals 2 times t. And of course, that's what we know now as the what? If we were to take the derivative of t squared using the power rule, what do we get? 2t. And he gets it without the limit. He doesn't set up the limit. He doesn't really use the power rule. He just expands this little quadratic. Now, what's wrong with Newton's method of fluxion? Well, first of all, if he's calling the fluxion of t squared 0, then the only way the fluxion of t squared is 0 is if the fluxion t equals 0, or the other factor, the fluxion of t equals 0. But wait a minute, it's the same factor. So unfortunately, by saying the fluxion of t squared is 0, he's also saying the fluxion of t is 0. And why is that a problem? Because in his ratio, then, what is he doing? He's dividing by 0 right there. And it's actually division by 0. Now, the mathematicians of the day were in awe that Newton got away with division by 0. And why did he essentially get away with it? Why did people turn a blind eye to the fact that he did divide by 0? It worked. It worked. Yeah, pretty impressive. So people now had a way, like Galileo had a way, well, he would have had a way had he lived longer, to calculate the instantaneous rate of change by calculation. And it wasn't until much later that the idea of the limit came along that kind of got rid of the problem of division by 0. We know now that he really wasn't dividing by 0. The idea of the limit is that t is approaching 0, and we have a way to kind of cleverly now circumvent that. So this was Newton's fluxion. He divided by 0, and he used kind of the dot notation, which we don't really use anymore. But we still get to use Leibniz notation. So they both had the same idea. The differential of y in Leibniz notation was an infinitely small change in y over an infinitely small change in t. Newton just called his a fluxion, which kind of symbolized change, right? Something that's fluctuating over time. So anyway, there's kind of a historical aside, Newton's fluxions. The limit, well, God, that's a good question. I think Augustus Cauchy first referred to the limit, if I'm not mistaken, in some of his math writings. Although he didn't use the limit notation per se, he was the first guy to introduce the idea and said the words limit. Yeah, and this was afterwards. Yeah. 100 years or so, a couple hundred years actually. Yeah. And I don't know. I want to say it was a French orphan bastard by the name of d'Alembert. He was abandoned on the doorsteps of an abbey, and he was raised by the monks there. And I believe, if I'm not mistaken, again, that he came up with the idea of the limit, or he contributed to the idea of the limit. So it was kind of like a joint effort that it collaborated into the limit. So anyway, we could Wikipedia those details and do some fact checking. Yeah, but the limit did avoid the problem of division by 0, and that's what we use today now, the idea of the limit. Okay, so let's talk about what some of these rates of change are, and we've kind of alluded to this already, and this is what you study in your physics class. This one little equation right here ties in the position, velocity, and the acceleration at an instant. The instantaneous acceleration is the instantaneous rate of change of velocity, and the instantaneous rate of change of velocity, or the instantaneous velocity, sorry, is the instantaneous rate of change of position. And therefore, the instantaneous acceleration ends up being the second derivative of position. Those are your three kinematic equations. And if you start with position, you can just take derivative, and get your velocity and acceleration. Displacement. Let's review displacement. Displacement is your net change in position. Your net change in position. If I stand up here and I go 2 steps to my left, or your left, and 2 steps to my right, I have traveled 4 steps, but my displacement is what? 0, because I'm right back where I started. It's S of B minus S of A if S is your position. It's your final position minus your initial position. If you do S of A minus S of B, you don't get your displacement. Displacement is a vector in that case, right? The sign tells you of your displacement how you were displaced. If it's a negative number, you ended up to the left or below where you started. And if it's a positive number, you ended up to the right or above where you started, depending if we're moving horizontally or vertically. The distance traveled, this one's kind of interesting. The distance traveled right now is going to be the sum of the absolute values of the distances between turning points. And let me show you what I mean by that very quickly. Let's say I have a graph of a position function, and it looks like this. I want to figure out the total distance I traveled. Well, if I just do S of B, if this is the function S, minus S of A, I'm going to get my displacement, right? But if I want the distance traveled, I need to figure out basically how far I traveled from here to here, yes? And then I need to figure out how far I traveled from here to here, and then I need to figure out how far I traveled from here to here. Okay, so I could figure out where it turns around, and I could do final position minus initial position to that high point, take the absolute value just to bless you, make sure it's positive, and then find the displacement between this high point and this low point, take its absolute value to make sure it's positive, and then take the displacement between this low point and the end point, take the absolute value of it to make sure it's positive. And that'll give you the total distance traveled. The average velocity is the average rate of change of position. You don't need calculus for that. That's displacement over elapsed time. It's the difference quotient right here. S of B minus S of A over B minus A. It's the slope of the secant line. But the instantaneous velocity at time little t, is, of course, the instantaneous rate of change of position. It's the slope of the tangent line. Speed, this one's important. Velocity is a vector, just like displacement. Negative velocity means that the distance is decreasing, and positive velocity means the position or the distance is increasing. But the speed is just the magnitude of velocity. It's the absolute value velocity. It's a scalar quantity. Okay? It's non-directional. Now, when we talk about speed increasing or decreasing, that's a really important thing. Speed is going to be essentially increasing when velocity and acceleration are working together. Speed is going to be increasing when velocity and acceleration are working together, both positive or both negative. It's like running somewhere with a tailwind behind you, right? It's propelling you forward, and it doesn't matter which direction. Speed is going to be decreasing if velocity and acceleration are working against each other. That's like running into a headwind. It's going to slow you down a little bit. So one's positive, one's negative, versa versa, either one. That's kind of the idea. When we make the argument, we will say how the signs are. Speed is positive, or speed is increasing because velocity is positive and acceleration is positive. But just keep that in mind. Acceleration and velocity. When they're working together, speed is increasing. When they're working against each other, speed is decreasing. So you need to look at two things for speed. If you're talking about the velocity, though, increasing, the velocity is increasing when its rate of change is positive. That's when acceleration is positive. Velocity is decreasing when its derivative, its rate of change, is negative. And the direction of an object changes when your velocity changes signs, from either positive to negative or negative to positive. And believe it or not, it doesn't even have to pass through zero necessarily to do that. If something has a positive velocity at one time and immediately to the right of that time, it's the opposite sign, velocity change signs, the particle changes position. We'll work problems like that. So this is just kind of some of the key points, some of the things we're going to be looking at as we look at these problems. Let's try one out. Example 6. A particle. A particle moves along a horizontal line. So that's kind of important. We're moving left or moving right. So immediately in my mind, I'm thinking, okay, if the velocity is positive, I'm moving to the, or the particle's moving to the right. If the velocity is negative, we're moving left. It's always fun to pretend you're the particle, huh? I'm going to refer to it in the first person. I'm moving left, I'm moving right. I'm the particle. So that its position at any time greater than or equal to 0, that's kind of important. So negative values are off limits, right? Sometimes they're not. Sometimes we can extrapolate backwards. But in this case, they're off limits. It's given by this function. So typically, if we're moving on a horizontal axis, the position function will be called x of t. If we're moving on a vertical axis, it'll be called y of t, where x is measured in feet and t is measured in seconds. Okay, so we have units. We now have the responsibility of putting units on every single one of our numeric answers. Got it. Part A, find the displacement during the first 3 seconds to explain its meaning. Displacement, that's the net change in position. You want to get in the habit of labeling your expressions. So I'm going to just label it displacement. Okay, during the first 3 seconds. What time values is that going to involve? From the first 3 seconds, that should be from 0 to 3, right? So it's going to be x of 3 minus x of 0. Where it ended at 3 minus where it started at 0. And, of course, we can evaluate that now. That's going to be 3 squared, which is 9, minus 12, and then plus 3. And then if I plug in a 0, I get minus x of 0, which is 3. So I end up with negative 3. And the units are what? Feet, right? Feet, we're measuring in feet on the distance. So what does this mean? Well, let's go ahead and write the sentence. On the interval, or how about just from? That's a little bit shorter. From 0 less than or equal to t less than or equal to 3 seconds, You want to include units always in your explanation. The particle, how about ended up? Positive 3 feet to the what? To the left. Yeah, let me scoot all this over. To the left of its starting position. Ended up 3 feet to the left of where it started, or something to that effect. Does that necessarily mean that it only traveled 3 feet the whole time? It only traveled 3 feet? No. It could have traveled 100 feet just to net 3 feet to the left, right? So again, that's all displacement is. We took its pulse at the end, we took its pulse at the beginning, and we just found out its displacement. It's net change in position. All right, find the average velocity of the particle during the first 3 seconds. Explain its meaning. Does average velocity require calculus in this case? No, because this is the average rate of change of position. And we have the position function. So the average velocity is going to be the difference quotient, right? It's going to be the displacement. So x of 3 minus x of 0 all over 3 minus 0. Now get in the habit of showing your difference quotient. That's going to be worth a check. Even though we know 3 minus 0 is 3 in the bottom, make sure you show the 3 minus 0. Now, of course, if this were a follow-up question to Part A, didn't we just find the numerator in Part A? Yeah, so we can import it now. So we got negative 3 over 3, which equals negative 1. And what are the units? Feet in the numerator divided by time, seconds in the bottom. So that's the numeric answer. Now the explanation would be, again, during the first 3 seconds, or during 0 less than t less than 3 seconds, comma, the particles, you could answer this 2 ways. We have an appreciation of what velocity means, don't we? So you could say the particle's average velocity was negative 1 feet per second. That's fine. But you can also say the particle's position was what? Increasing or decreasing? Decreasing. Somewhere you got to add that little phrase, on average, I'm going to insert it here, on average, by 1 foot per second. So this is why we started yesterday with writing those sentences with the whole DM. We're interpreting the answer with units. So again, how are you going to know whether to answer it in terms of the particle's velocity versus the particle's position? The question will usually say. It'll say, explain what this means in terms of the particle's position. I didn't say that here, I don't think. Did I? No, I just said explain its meaning. So we'll analyze both cases. Explain what it means in terms of the particle's velocity. Either one. Did you say it was moving to the left? Oh, yeah. You could say it was moving to the left on average. Does that mean it was moving to the left the whole time, though? That's where you'd have to be careful. I'm not sure if I like that wording. The particle was on average moving to the left, maybe. If you stick it in front of there, it kind of qualifies moving to the left. Because, again, it doesn't mean it was moving to the left necessarily the whole time. We're just saying the general trend was it was moving to the left by 1 feet per second. Whenever you're talking about it in terms of the position, it's always good to kind of just stick to the bland answer of saying whatever you're measuring was increasing or whatever you're measuring is decreasing. It's the safe way to go. Okay, find the particle's initial velocity and its velocity at 3 seconds. Explain the meaning of each. Okay, the initial velocity, well, that's going to be the velocity at 0. And the velocity at 3, that's the velocity at 3. How do we find the instantaneous velocity? If we have the position equation, the derivative. Now, here's a nice trick for a free response. Put x prime of t. They gave us the equation x up above, right? If you put x prime of t, that's all you have to show. But it's nice to then give it a new name, v of t. Now, if you need to use it later on, you can just refer to it as v of t. And it's labeled. We can clearly see how you got v of t. So what is the derivative of t squared minus 4t plus 3? 2t minus 4. Okay, so this is a pretty typical thing. X prime shows you what you're doing, or shows us what you're doing with the derivative. V gives it a new name. Kind of helps you understand what's going on. And now you could either say x prime of 0, or you could say v of 0, Or you could say x prime of 0 equals v of 0. You could use both, or either one. It doesn't matter. And when you plug in now, you get -4. What are the units? Feet per second. You'll always lose a point if you don't put units, in my class, on those numeric answers. Sometimes on a free response, the unit is tied to the right answer, which means every time there's an answer with units, if you don't have the units, you lose the point, even if the number's right. And sometimes the units total are worth 1 point on the whole thing. So if you miss them once or you put the wrong ones, like you put furlongs per fortnight or something instead of feet per second, you'll lose only 1 point. But you never know, so you put them every time. All right, and then v of 3, let's go ahead and find that. V of 3, or x prime of t, that's going to be 6 minus 4, which is 2 feet per second. Now I'm just going to say what these mean. I'll do the first one, you do the second one. At t equals 0 seconds, comma, the particle is moving, now we could say to the left, right? Because we know at that instant it's moving to the left. At t equals 0 seconds, the particle is moving left 4 feet per second. Okay? Or you could say the particle is initially moving 4 feet per second to the left. Something like that. You can use their word, it said initial up here. But again, t equals 0 seconds is good. All right, what would this one be? At t equals 3 seconds, comma. Yeah, it's moving right 2 feet per second, or moving right at a rate of 2 feet per second, or moving right by 2 feet per second, or the particle's speed is 2 feet per second to the right, whatever. There's lots of ways to do that. But notice that when you write the sentence, you interpret the sign. When you write the sentence, you interpret the sign. So you interpret it as a direction and a magnitude. In the numeric answer, though, the direction and the magnitude are all tied into one number. Yes? Okay, good. Part D, find the acceleration at 3. Acceleration, that's the instantaneous acceleration. How do we get instantaneous acceleration? It's derivative velocity. Now, if you've called the function above v of t, you could say v prime of t. And, of course, you can give it a new name, a of t, if you want to. If you never called what's up above v of t, don't use v prime of t here. You would have to just stick with x double prime of t. It's all good. I like renaming things. It shows understanding, and it really helps reinforce it for you. So what would be the derivative of 2t minus 4? 2. Now, notice it's a constant. Have you answered the question yet, though? If you just say, so the acceleration is 2? No, because this is still a of t. You need to now say a of 3 then equals 2. Now that answers the question. And what are the units? Feet per second squared. Okay. Now, to answer that, again, we have an appreciation of what acceleration is. So you could say at t equals 3 seconds, here's the two different versions, comma, the particle's acceleration is 2 feet per second squared. And that would not be wrong. That would be answering the question in terms of the particle's acceleration. But if it said answer the question in terms of the particle's velocity, then what you'd have to say is, oh, acceleration is the rate of change of velocity. So at t equals 3 seconds, comma, the particle's velocity is what? Increasing or decreasing? Increasing, because it's a positive number, is increasing by 2 feet per second per second. That's the way you'd want to write it. So for every additional second, the velocity is increasing by 2 feet per second. So read very carefully. How does it want you to explain it? In terms of the acceleration or in terms of the rate of change of velocity? All right, now at t equals 3 seconds, is the speed of the particle increasing or decreasing? We said the velocity was what? We just said right here the velocity was increasing. Does that mean the speed is increasing as well? Right. That the velocity increasing doesn't necessarily mean the speed is decreasing. Okay? Anytime it says speed, you must look at two things. You must analyze the velocity and the acceleration. Are they working together or are they working against each other? So here's what you would do. Let's analyze v of 3. Since we've labeled the function v, we can do that. And let's figure out what a of 3 is. And since we've labeled it as a, we can do that. Otherwise, you're going to compare x prime of 3 to x double prime of 3. Well, we already found v of 3, didn't we? It was up here, positive 2. The fact that it's positive is what matters. So if you want to say equals 2, which is greater than 0, or if you just want to say greater than 0, it's all about the inequality. Now, a of 3 was positive 2, so that happened to be the same. So that's also greater than 0. They're both positive, right? So what? The speed is increasing at t equals 3 seconds. Now, I used to have my students say, since the velocity and the acceleration are the same sign at t equals 3, the speed is increasing. Because then it wouldn't matter if they're both positive or negative, but you're required to show what the sign of each of them is. So when you just say that they're greater than 0, and then you come up with so, that's fine. You're saying basically since they're both positive, the speed is increasing. Now, if you don't show the inequalities, would that be enough to say v of 3 equals 2 and a of 3 equals 2, so the speed is increasing? No, because someone might look at that and saying, oh, okay, so only when they're both 2 will the speed be increasing. If they were both 3, I'm guessing it wouldn't work. But by saying that this, or you could say since, that's another nice way to tie that into your argument. Since that, comma, and then you can get rid of this and just say the speed. So however you want to phrase the argument. This is your mathematical justification right here. It's the evidence. Then you give some kind of claim. All right, during what times is the particle moving to the right and then to the left? When is the particle moving to the right? How are we going to figure that out? The particle is going to be moving to the right when its position is increasing, right? And its position is increasing when its rate of change is positive. So it's going to be moving to the right when what is positive? What's the rate of change? V of t. And again, because I've called it V of t, I can just say V of t is greater than 0. All right, so let's come back up and find our V of t equation. V of t was 2t minus 4. So that's when 2t minus 4 is greater than 0. That's an inequality, right? That's linear. Can I solve that algebraically? Yeah. So that's when 2t is greater than 4. That's when t is greater than 4/2, which is 2. Now it's my final answer. I'm going to put seconds. And notice if I say right, I can do that, but it's probably best to summarize it. So the particle moves right for t greater than 2 seconds. Get in the habit of summarizing it. And I guess it's moving left. Again, labeling our work. That's going to be when the velocity is negative, right? So if I set up that inequality negative, that's also linear. Well, that's going to be t2 is less than 4. That's when t is less than 4, or 2, sorry, 4/2 maybe. Now, if I stop there, this is where I get into a problem. So the particle moves left for t less than 2 seconds. This is where the typical student will lose a point. What's wrong with that? The line, the graph of 2x minus 4 is below the x-axis everywhere to the left of 2, all the way to negative infinity. But this is a problem that deals with motion. We have a relevant domain, don't we? What did it say at the very beginning? T is greater than or equal to 0. When they tell you that in the beginning of the problem, or when I tell you that, that's for a good reason. It means that you're probably going to have to consider that somewhere in the problem. So if I just say down here less than 2 seconds, that's going all the way past 0 to negative infinity. I better put the lower bound there. And now you just spared yourself a point. What's that? Well, yeah, let's talk about what is it doing at 2. If it's moving right to the right of 2 and left to the left of 2, you would call 2 a stationary point, right? It's at that instant, it's technically immobile, and it's because our function is a polynomial and it's continuous. But what I said earlier is that It doesn't have to be immobile at any point in order to change directions. Now, anything in the real world that we know of, when it changes directions, it can't do it instantly. It can't be going to the right in one instant and left in the next instant. Even if it does it very, very quickly, if you slowed it down enough, it would be decelerating to zero, motionless, and going like that. But if you had a velocity graph with highlighter, I meant to do that, and let's say that it was, let's say here at 3, it was positive and it was negative. Would the particle change direction at 3 based upon this graph?
Pardon the interruption. Teachers, please turn your TV.
When the velocity is positive, the particle is moving to the right. When the velocity is negative, if this were the velocity graph, when the velocity is negative, it would be moving to the left. So at 3, it changes from moving to the right to the left. Would it change directions at 3? Yes. Does this one actually pass through 0? No. Now, what changes directions like that? I have no idea. Subatomic particles, maybe? That's the only thing I could think of, things that move that fast. But I think even then, if you could slow it down. True, right. Yeah, so if you get into quantum physics and stuff like that, that's kind of, I don't know. Apparently, according to quantum physics, I can lean on this wall, and there's a chance that I can fall through into this. Yeah, and it's not because of shoddy construction. I would actually go through the wall. There's a slight probability that I can go through it. Huh? And I'm also not touching it. The what? Oh, really? Okay, and there's a parallel universe right in front of my face. There is. And I just can't see the people living there. Right. So, in this case, because our velocity function is a line, which is a continuous function, for this particular function, yes, the velocity has to pass through 0 as it changes directions. But keep in mind that just because the velocity is 0 doesn't mean that something changes directions, right? I could be walking towards that board right there, and now I'm getting tired because I'm out of shape. My velocity is what? 0. And now I'm going back towards the board. I'm re-beginning my trek, my quest anew, okay, after that short break. Did I change directions? No. Okay, so what are we looking for? The particle will change directions only if the velocity does what? Changes signs. Okay. Now, do you think we have to say how the sign changes? Yeah. It doesn't really matter if it changes from positive to negative or negative to positive for there to be a change in direction, but we still have to say how. So, what times is the particle moving right? Okay, so the last one. At what time does the particle change direction? Justify. The particle changes direction. The particle changes direction, and I'm borrowing space in the next one here. At t equals what? At t equals 2 seconds, don't forget the unit, since v of t changes, this is how we're going to answer it, v of t, the function, the velocity function changes from what to what at t equals 2? From negative to positive, good. From negative to positive at t equals 2 seconds. We're going to say it again, and you're going to get used to that. It almost sounds redundant. You're saying, here's where it changes directions at t equals 2 seconds, and then as a separate thing, since that happens to also be the time where the velocity changes from negative to positive. Now, how do we know it changes from negative to positive? Is that right? Or is it positive to negative? We know that it changes from negative to positive because we just did the calculations up there, and you can also just realize it's the slope of a line with a positive slope, yeah? So it's negative, here's v of t. It changes from positive to negative. You don't want to mess it up and say that you know that's where it changes because v of t changes from net positive to negative there. Don't do that. That messes it up. You have to say how it changes. So this would get full credit. You would get 1 for there and 1 for there in my class. 1 for the answer with units, 1 for the justification. So you're always going to get in the habit of saying that the function v of t changes from positive to negative or negative to positive. You'll get used to that. All right, and then the last little piece. Find the total distance it travels during the first 3 seconds. Are you exhausted as a particle? Find out the total distance it travels. We know up here the displacement from part 1 was negative 3 feet. Let's see if we could figure out what this graph looks like very quickly here in the time that remains. I know it's a parabola that opens up, yes? X of t. What's the y-intercept? 3. Can I figure out where the vertex is very quickly? Yeah, I could take the derivative, which I already down below, I called it the velocity, and I can set it equal to 0, 2t minus 4, but we already discovered that is at t equals 2. So right here, t equals 2 is the vertex. And what was the function value at 2? Did we ever figure that out? What is x of 2? So we can figure out the y value. 2 squared is 4, minus 8 is negative 4, plus 3 is negative 1. So I'll bring that 2 up there. Call this negative 1. And if that's 2, then 3 would be right here. There's 1. What is the y value at 3? Did we figure that out? I think we did that over here. X of 3 was equal to what? It was this. 9 minus 12 is negative 3 plus 3 is 0. So it ended back up there on the axis. So just with those 3 points, the y-intercept, the vertex, and where it ended up, I got that little piece of the parabola. That's our relevant domain. I want to figure out the total distance it traveled. So here we go. The total distance, or just the distance, it's going to equal the absolute value of, if I can figure out the displacement in between the turning points, notice it turned around right here at 2. That's going to be s of 2 minus s of 0. And I've taken the absolute value just to make sure it's positive, because I want it to be the total distance traveled. And then plus, I'm going to add to that the displacement from 2 to 3, so s of 3 minus s of 2. Okay, so that'll tell me essentially how far it traveled going down and how far it traveled going up. And it'll make both of them positive, and then we'll add them together. Okay, so now I just have to do a couple of calculations, and I'll work upwards here. S of 2, did we already figure that out? It was negative 1. And then S of 0, we know that to be 3. So you can almost just look at the y values here, right, because we've calculated them. So from 3 to negative 1, it went down how many units? 4. But it was a total of 4 units traveled, and that's why we get a 4 right there. And we already know the answer to this one. In that last second from 2 to 3, it goes up from negative 1 to 0, so it's a distance of 1. But let's do the calculations, because in general you won't have the graph. So S of 3, remember, was 0, minus S of 2 is negative 1. And if you calculate that, that's 1. The absolute value is 1. So the total distance traveled was 5. And again, looking at the graph, starts at 3, goes down to negative 1. That's 4 units down. And then in the next second, it goes up from negative 1 to 0. That's another 1 unit. 4 down plus 1 up makes 5 units total. That's the total distance. What's wrong with my numeric answer? Feet. So here you go. The particle ended up traveling 5 feet to net 3 feet to the left of where it started. Okay? No big deal. All right, and there's a typical particle motion question. That's example 6. Fun. Any questions on that? All right, should we start the next example, or that's probably calling it a day here. Tomorrow we'll start with, instead of an equation, we'll look at a graph. That's fun. If you thought today was fun, tomorrow is also fun.